Welcome to another Coding Like Mad Matlab tutorial. Today is part 1 of our neural network tutorial series, Training Neural Networks for Regression. If you want to catch future parts of the series, don't forget to subscribe to the channel. Today we're going to be talking about neural networks in Matlab. If you want to follow along at home, you're going to need a license for the Matlab Neural Network toolbox, and perhaps this video will help you see if that's a good match for you. In this video, I'm going to focus on neural networks in Matlab, but we need to talk just a bit about neural networks first. So what is a neural network? Put simply, it's a calculation which is modeled after biological nervous systems. Mathematically, it's just a set of linear algebra calculations filtered through activation functions. Here, for example, is MATLAB's representation of a one-layer network. For a regression network, we want to train the network to map an input, x, to an output, y. In this one-layer network, there are 10 neurons in the single layer, each of which connects to the input and the output. This type of network is called fully connected because all of the nodes connect to all of the nodes on adjacent layers. The biggest challenge in general is training the weights and biases in these layers, but with the advent of massive parallel calculation platforms and GPU acceleration, this type of calculation has become possible even for networks with many thousands of inputs. Here, though, we're just going to have one input and output. Maybe you find this concept simple, but it's actually incredibly powerful, driving some of the most futuristic applications that we have in our world today, like self-driving cars and computer vision. So, how do we go about training neural networks in MATLAB? Well, first we're going to need some data for our network to learn. To do this, let's introduce a nice complicated function. We'll have some polynomial parts, some trigonometric parts, and an exponential part. We're also going to bring in some random elements. First, let's make the sampling in x random between -1 and 1, and then second, we're going to introduce some noise. Just for fun, I've let the amplitude of the noise vary with location on the function. Let's visualize this random data samples with the underlying function. You can see it's a pretty noisy representation of the underlying function. Next up, let's go ahead and create and train our neural network. If we look at this next section of code, you can see the first thing we do is create the feed-forward network. The argument here is specifying that there is one hidden layer with 10 neurons in it. Now that our network is defined, we can go ahead and feed our data in for training. There's a ton of possible options here. Do you want to train with parallel CPU calculations or use the GPU? What algorithm are we going to use for training, and what parameters should the algorithm use internally? The good news is, all the defaults are fine for what we want to do here. Let's take a look at the training dialog first. This dialog shows the status of the neural network training. Because we are doing such a tiny network with only 100 input data points, it finishes nearly instantly. Let's take a bit of time and break down this dialog. At the top, we have a visualization of the network we're using. Next, we have a section giving us information about the technical aspects of the training. Are we running a CPU or a GPU? What type of optimization is being used? And how is the data divided between internal validation, training, and test sets? Last, we have a section we really care about. How close is the network to being finished training? In this case, we only had 0 seconds to wait, but imagine if you had to wait 20 or 30 minutes. You would spend a lot of time looking at this section. It includes how many iterations of the training have occurred, 10 in this case. How long did it take? 0 seconds because it's such a simple problem, as well as how well is the performance of the network actually doing at this point. The validation checks indicate that the network in this case is fully converged because it did 6 in a row and all 6 of them said that additional training was making the performance worse. This seems like a bit of a funny thing for the system to be doing, but what it's really doing is continuing to train until additional training is actually hurting performance. It's a guard against overtraining. In the bottom section, you'll additionally see that there are a number of buttons that allow you to pop up new dialogues and explore things in more depth. We won't go into additional depth on these buttons, but you should play with them if you are working with neural networks a lot. Okay, so how did we do? Let's take a look. You can definitely recognize the function, but let's be honest, it looks a bit ugly. If you squint a bit at the data, you'll notice that the network is actually following the underlying trends in the data. Each strange step it makes is corresponding to a quirk we introduced with the noise. This tendency to follow every quirk in the data is called overfitting or overtraining, and we generally work very hard to avoid it. Here, it's a bit hard to say that this is the wrong thing for the neural network to do. We know the right answer is a smooth function, and this isn't a smooth fit that it's producing, but we're using prior knowledge in order to come to that conclusion. For the neural network, this is a very reasonable thing for it to do. Additionally, if we had included a high-order polynomial fit, we would have seen the exact same thing. So overall, it's not that bad a fit, but let's explore this a bit more. The first thing you need to know about neural network training is that it's not deterministic. We used random weights when we started our training, so if we retrain the network, we get a different answer, as you can see here. One approach to avoiding issues with overtraining is to average many of these networks together. This is called creating an ensemble model. Next, let's take a look at what happens if we go to a much more complicated neural network. This one will have 6 hidden layers with many more neurons in each layer. For comparison to the original training time, I've increased the number of data points a bit so you can watch it train. I've sped things up a bit though because you didn't want to wait the full minute for it to finish. This model again is not smooth, but you can see that it is again picking up on very real, albeit noise-induced features in the data. In general, overtraining gets worse the more complicated the network is. Conversely, had we gone to even a single layer with only 3 or 4 neurons in it, it actually fits the data in the original data set extremely smoothly, but we're cheating a bit by using prior information when we do that. On the other hand, if we go to far more data, the neural network will come to the right answer, as you can see when we go to 10,000 input data points. Neural networks will tend to overtrain when there is much less data than parameters, so understanding how to balance the data needs with model complexity is important to getting a good result. Ultimately, the real strength of neural networks is their ability to deal with complicated functions which we don't really have a method to describe. Things like object detection for computer vision, or playing games like Go that require sophisticated thinking beyond what we can easily put in a single equation. If you like this tutorial and want to see more like it, you should consider liking and subscribing to the channel. If you have more questions or comments about this video, or suggestions for future tutorial topics, go ahead and put them in the comments below, and I'll get back to you and we'll see what we can do about making more content like this for you. Have a good day, and I will see you next time.